Good afternoon, everyone. Thank you for joining for this session. As you all know, this is the weekly sessions we have uh, after these NPTEL lectures, and this is the session for NPTEL course Solid State Physics. The course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am a TA for this course. I am Mrinalini from School of Physics, University of Hyderabad. These sessions we have every Saturday, 3 to 5 p.m., where we mostly focus on doing numerical problems related to that week's lecture content. And also, we sometimes, if there's some important or some specific topic that needs revision, we discuss that as well. And if you guys have some doubt from in this week's or earlier uh, week's topics also, you can ask. Okay, so let's start today's session now. So recommended books you all know are these four, useful to get the content related to all the topics we are covering in solid state physics in this course. And yeah, so last week we started discussing magnetic properties of solids under the solid state physics course. And so in the lecture, the things that were discussed were some basic terminologies when we start discussing about magnetic properties of any material. There are some terminologies like magnetization or magnetization field, magnetic field induction, and then permeability, susceptibility. So terms like this, which we understood, then we moved on to, and in the lecture, uh, subsequent things were what is the origin of different type of magnetism that we see in the materials around. We had discussed about paramagnetism and diamagnetism. Now this week's content was mainly about the origin of ferromagnetism that we see in ferromagnetic materials. And yeah, so last week we had discussed about what is magnetizing field or intensity of magnetizing, or what is magnetic field flux density, and what is the difference. Although we see every time in these topics that B and H are interchangeably used, sometimes we say the usually how I explain for you to be clear about this is that the field that we apply, because when we know a current carrying conductor, it has magnetic field generated around it. So the field that we apply by supplying current, the field that is generated, that is the field we use to magnetize some material. So we say we apply H, and the unit is ampere per meter, and then the field that is induced in this body because of this effect of the field that we are applying, that is proportional to the field that we are applying, and the proportionality constant is permeability. So it's like how easily the material can be magnetized. But still you will find that sometimes we just use for magnetic field we use B symbol. And this is vector, we use B. So, and the unit is Tesla or Weber per meter square. So don't get confused. But for clear understanding, this is the meaning of H and B, but it may be sometimes used interchangeably. So don't get confused. There is this not standard, these things are not standardized, and thus this mixing is there always. But I think in questions it would be clear if they are what they are talking about. And as you can see in this graph, that this is, as I said, we apply H and then we get some response as B. So this is what the B versus H graph symbolizes. Other things, yeah, we had seen that this permeability that we say, the ability of a material to get magnetized. The permeability, it can be negative, and when it's negative, that means the substance is not allowing the magnetic field lines to pass through it. This is usually shown by diamagnetic materials. And the magnetic permeability, when is more than one, that is characteristic of paramagnetic material, where the more magnetic field lines tend to pass through it, and thus these materials get easily magnetized. And then we have materials for which permeability is large. Those are ferromagnetic or ferrimagnetic materials. So these were the things we had discussed, and then permeability and susceptibility also we had understood what are the units, how they vary for these different materials. So, and then the derivation related to origin of diamagnetism and paramagnetism. Derivation we had not done because you can find that in the lecture itself. So further we had focused on the numericals. So now in this week's there was, as I said, there, or you would have seen, there was a topic on origin of ferromagnetism. So again, we will not focus on the derivation for that. In fact, we'll mainly be doing some numerical problems, but okay, we can have just quickly you can see what were the different kind of magnetic materials. So one first that we had seen was diamagnetic material, which we consider in classical model. We say that any atom has electrons revolving around it, because of which there is orbital angular momentum, and that gives magnetic moment to that electron and to that atom. Because of this orbital angular momentum, we get diamagnetism, which always opposite to the field that we apply. So if there is, there is orbital angular momentum because of this motion, and then there is magnetic moment, and when we apply a field, then this is opposite to this field, and that's why the magnetization versus field graph for diamagnetic material is like this. It passes through the origin. What it means is we are applying some positive field, some kilo Oersted, some Oersted, and the magnetization is negative. So I'm applying field and the magnetic moment is in opposite direction. This is what happens for diamagnetic material. And the susceptibility for diamagnetic material also we have seen that it's independent of temperature. Whereas next type of magnetic materials are paramagnetic materials. We say that there are unpaired electrons or effective magnetic moments in this, but they are randomly oriented in absence of field. They are randomly oriented, and thus there is no net magnetic moment in absence of any field. Till we are not applying any field, the magnetic moments because of unpaired electrons in the atoms, whatever this material is, its atoms will have magnetic moment, and if they are paired, then that will be cancelled out. But if there are some unpaired, because of that there will be these magnetic moments, but they are randomly oriented. So the net magnetic moment of that whole material, it comes out to be 0. But when we apply field, the field interacts with the magnetic moment and makes it align along to get minimum energy. And when we apply field, all these moments in this material, they align along the direction of field, and then when we measure, there is some magnetic moment of that material is not 0 anymore, but it gets some non-zero value. Thus, the MH loop for these kind of materials is when we apply field, the magnetization keeps on increasing. And if we apply negative field, the magnetization will be, if I apply field in opposite direction, then the magnetic moments will orient along this direction. So we say it's minus n. So the graph looks like this. This is the behavior of paramagnetic materials. And then it depends on temperature. If the temperature is more, means why the magnetization decreases, because if this is for some temperature T, the loop, the graph is like this, and versus its graph for paramagnetic material is like this. But if this is at some temperature T, if I increase the temperature to T1, then the behavior will stay same, but the loop may, the slope will be less. Why this happens? Because now, although the field that we are applying is trying to orient these magnetic moments along with it, but because I have increased the temperature, means I am supplying some form of thermal energy, which again leads to randomization of these magnetic moments. So now there is competition between this thermal energy, which is trying to randomize them, and then there is the field, which is trying to align them all in one direction. And that is why now there will be requirement of to apply more field to make all of them align, and thus to increase the magnetization. And the relation is that it's inversely proportional. Susceptibility. The next type is ferromagnetism. These are materials for which the origin was what was discussed in this week's lecture. There is classical model called Weiss theory model, Weiss molecular field model is the name of the scientist, and he had talked about something known as molecular field. Because what happens for ferromagnetic material is, unlike paramagnetic material where we see or where we say that although there are unpaired spins, unpaired electrons, and thus there is there is magnetic moment, but overall for that material, because they all are in random direction, so overall magnetization of that material is zero until we apply some field. In ferromagnetic material, even if we don't apply any field, any magnetic field, the materials still will have some magnetization, net magnetization, because the sum of the magnetic moment without even applying field, some magnetic moments are still aligned, and thus we get magnetization or we get net magnetic moment, some value which is not zero. So to explain what could be causing this alignment without even applying any magnetic field to make them align, Weiss gave this hypothesis that there is some field inside the material, which, so we are not applying any external magnetic field, but there is some sort of internal field which is making some of the magnetic moments to align or to get along each other. And he said that that internal field is proportional to the magnetization of that material. But if you would see, or you would have already seen, when we derive based on this model, the magnetization, no, sorry, the this internal magnetic field, when we derive it and get what could be the internal field, magnitude of the internal field, it comes out to be a huge value, something like 10 to the power 3 Tesla or something, which is a very big value, because even 1 Tesla is difficult to make, I mean, to generate, and 10 to the power 3 Tesla is very, very big. And just of because of dipole interaction, this much is not possible. And so this, although few things were this model could explain, but this was very far away from what can actually happen. So here this model had failed, and then we had got another model based on quantum mechanics. Now this was classical model based on quantum mechanics, because here we considered spin angular momentum, which is a quantum mechanical uh, concept. Because unlike when we explain orbital motion of electron in classical mechanics, the spin may be a misguiding term, because the electron is not actually spinning on its axis. It's not possible. Through some calculation, that is not possible, and it's not happening. It's just because it was thought maybe the electron is spinning after orbit. First, it was considered that the electron is orbiting around the atom or around the nucleus, and orbital angular momentum was given. Similarly, it was thought that maybe it's spinning on as well, and thus spin angular momentum or spin term was coined. But later on, it was understood that it could not be actually spinning. So basically, the spin angular momentum or spin concept of spin is quantum mechanical origin. And this spin interaction, that every this dipole moment they are interacting, and because of their interaction, exchange interaction this is called, because of their interaction they keep each other aligned. Because if they'll keep each other aligned, there is term for this, that if they are aligned in one direction, for some materials, if they are aligned in the same direction, their energy will be potential energy will be less. That means they will be stable. Whereas for some materials, if they are kind of anti-parallel to each other, then their energy will be less. So based on this Heisenberg exchange interaction concept, uh, the derivation is kind of able to explain why we have in some materials showing ferromagnetism, where the magnetic moments are parallel to each other and the net magnetization is non-zero. And we have some material called antiferromagnetic material, in which the magnetic moments are not all parallel, but they are anti-parallel. So net magnetic moment becomes zero in absence of field. The magnetization is zero, because for these material, the, the when the moments are or the spins are anti-parallel, they are more stable. That is, I think this in detail will be discussed in next week. I think these things, and domain concept of domains and domain walls also. So anyway, so this is how. So yeah, classical model was not able to explain this well, and then this spin concept and exchange interaction gives us the reason why they are existing along each other, because one spin influences the direction of another spin. And so like this will be influenced if I am considering single linear chain of spins or magnetic moments. Then these, for this atom, this spin, these are the neighboring atoms, and it will get influenced by these. So not from any third or fourth spin. So they are just they have to be immediate neighbor to be influencing their direction. Okay, so let's not go in detail here. So for ferromagnetism, this is what happens, and the Mh loop, if the sample is not magnetized and you start applying field, you will see something like this going on. After some time, it saturates, because all the material, when they get along some direction, I mean, all of them, this ferromagnetic material saturates faster because they are aligned in one direction. But this is okay. This was M versus H, and if this is at some temperature T, then again what happened with the in case of paramagnetism that we were saying, when we supply some thermal energy, then magnetic moments start getting randomized. Same thing happens here. If it is at some higher temperature, somehow I'm increasing the thermal energy of this system, then the magnetization keeps on decreasing. And for some temperature, it may not remain ferromagnetic. It will become paramagnetic. So because the thermal energy will be dominating this internal field or this exchange energy interaction, and because of that the moments will be randomized, and thus with field only they will get aligned. And thus at some higher temperature, say some, I don't know, let's call Ti. So if Ti is very large, then there is a, you must have encountered this in this week's lecture. This word is called Curie temperature. So Curie temperature for a ferromagnetic material is defined as a temperature above which the material changes into paramagnetic material. So above that particular temperature, the thermal energy dominate the exchange energy term, and exchange energy is not enough anymore to keep the moments aligned. So above Tc, they get the moments get randomly oriented, and the loop will not see like this. This is also just like in the beginning when we magnetize, because after once the ferromagnetic material, once when it's magnetized, then even if you bring, so here for diamagnetic or paramagnetic material, what happens if you take the, when the field is zero, the value is zero, when you take to positive, they become positive. If you bring the field to zero, again the magnetization will be zero. I mean, this is for diamagnetic, so it's like this. But for paramagnetism, if the field is zero, magnetization is zero. If you apply some field magnetization, you will get positive magnetization, and if you bring back the field, it will again come back to zero, because alignment is only depending on the field that we are applying. Whereas a ferromagnetic material, because we say there is already some interaction which is like orienting the moments in one direction. So once when we magnetize it, after that, even when you make the field zero, it will not come back, magnetization will not come back to zero. It will, so the graph actually, it's called MH loop. Okay, it becomes like this. This is minus H, this is minus M, and this curve is called hysteresis curve, or hysteresis loop, because it's a closed loop. So it's also called MH loop, hysteresis loop. Hysteresis is the word that tells that there is lag between M and H, because as we were seeing in the case of paramagnetic material, that there was no lag, in the sense as the H that we are applying, its magnitude was increasing, M was also increasing. They were proportional. But here there is lag, because you can see it's not, M is not following H. In the beginning, once when we magnetize it, because there is some concept of domain which will be discussed next week, so I don't want to go there, but initially we magnetize it once, after that it retains that magnetization, and even when I make the applied field zero, there will still be some, you can see there is still some magnetization even when the field is zero now. So magnetization is not following the H that we are applying, the field that we are applying. So there is lag between M and H. And now you see, first we apply, okay, it saturates, then I bring back the field to 0 and the magnetization is not coming back to 0, then I apply field in negative direction. So that's why we use the symbol minus. So we are applying this field now in opposite direction to the material, and after some particular value only the magnetization is coming to 0. The field is not 0 here, it has some negative value, some minus 10 orsted, minus 20 orsted, depend on the material. After we apply that in opposite direction, then the field, the magnetization of the material becomes 0. And then when we increase the field further in the negative direction, then the magnetization becomes negative, and then it increases, and then even this becomes maximum in negative direction. And then again, when we bring the field to 0, the magnetization still does not become 0. So there is lag between M and H, and that's why it's called hysteresis curve. Okay, and yeah, this is called retained magnetization remanence. This is called saturation because the magnetization of the material becomes maximum. At this point, all the magnetic moments are aligned along the direction of applied field, and then when we bring back to 0, again they start randomizing, but still not completely random, and thus there is still some net magnetic moment even when the field is 0. And then when I start applying field in this direction, the magnetic moments will start switching to opposite direction, and they won't switch immediately, only after applying some kind of magnitude of field in opposite direction, then only they will switch. And this field is called coercive field. We show it HC, and it is coercivity or coercive field. This is the value of magnetic field that we need to apply to switch or flip the direction of magnetization in a material. Okay, and this is called magnetization remanence because even after making the field 0, what magnetization remains in the material, that is why we call magnetization remanence. And this is coercive field. Then again, this is also coercive field in this direction. This is also magnetization remanence because we are just changing the direction of field. So for positive direction of field, this is magnetization remanence, this is coercive field. For negative direction, this is coercive field, this is magnetization. So this is how we, for ferromagnetic material, we get this kind of image graph, which is very different from what we get for diamagnetic material and paramagnetic material. And here also, depending on temperature, at some point of time it will not remain ferromagnetic, so it will be giving graph like this, which is like a paramagnet. And then we have, as I said, some material prefer that their spins or magnetic moments are anti-parallel. These are called antiferromagnetic material. Their image loop is difficult to explain, and because the magnetic moments are arranged like this, so immediately with applying field they will not start net magnetic moment, because in absence of field the magnetization is 0 here, unlike ferromagnetic material, because they are all cancelling each other out. The net magnetic moment here is getting 0. So there is some specific behavior of image loop. It's not very simple to tell, and we don't need to go to that extent. But yeah, I mean it is different, and that's okay. We don't need to understand that. But there's antiferromagnetic material also show high magnetization, and they also have temperature dependence. For them, and for them also we define a temperature above which they stop showing antiferromagnetic behavior. and that is called Niels temperature. Like Curie temperature for ferromagnetic material, this is called Niels temperature. Name is on coined on some scientist name, and above this Niels temperature, the material loses its antiferromagnetic, that is the exchange interaction that is keeping these magnetic moments anti-parallel to each other. That exchange interaction gets dominated by thermal energy. Again, for this lecture we don't need to go in detail for this. Yeah, the next thing is there are actually several types of magnetism. There is another called superparamagnetism also, but for our case we don't need to understand and to go all those terms. But one more we can discuss, which is called ferrimagnetism. How it is different from all the four, yeah, till we have discussed. So in ferrimagnetism also we have magnetic moments at anti-parallel direction to each other. But so in a way it's similar to antiferromagnetic, but there is difference that the magnitude, so the arrow, the what to say, the height or the length of these arrows are basically showing the strength of the magnetic moment here. Okay, the height or the length of the arrows is I'm using to show the strength of magnetic moment, the magnitude. So what happens for ferrimagnetic material is in one direction, let's say let's say it's x direction. Along x direction, magnetic moments are there, and then along minus x direction, we have magnetic moments anti-parallel to these. So they should cancel out, but they would not cancel out because the moments along minus x direction, their magnitude is smaller. So what to call? If I say this magnetic moments, or I can change the color. Let's say the anti-parallel one, these blue. So they are anti-parallel, but their magnitude is smaller. So magnitude of blue moments is smaller than magnitude of these red colored magnetic moments. Because of that, what happens? The net magnetic moment will be here. If you see magnetic moment in this direction, anti-parallel is opposite, but its magnitude is smaller. So net magnetic moment will be in this direction. Here also, if you see, net magnetic moment will be in this direction. So ultimately, there will be some net magnetic moment. That means there will be some magnetization. Right? Magnetization won't be zero even when field is zero. So in a way, it's similar to ferromagnetic material, because ferromagnetic material we saw that even in absence of magnetic field, the moments are aligned because of exchange interaction, and thus even in absence of field, even in absence of field, we have magnetization non-zero. So this ferrimagnetism has something like AFM, and it's in between AFM and FM. So it has non-zero magnetization, but its magnitude will be smaller because we are getting net of these two. Whereas for ferromagnetism, all were aligned in one direction, so we are getting higher strength of magnetization. So these are basic, just keep their meaning in mind clear. In theory and in models, we can go to a lot of detail, but we don't need to study for this course all of them in detail. So I think the origin of diamagnetism model for that was discussed, and for paramagnetism was discussed. Ferromagnetism it's been discussed, but I think only up to that has been discussed or is there in this course. So this just to keep in mind what kind of magnetism are there, the important kind, and how they differ from each other. Okay, so This is done. Till here, things are clear. Then I think we can start discussing numerical problems. Okay, let's start. Sorry, so I'm forgotten to give the options here. So first question is, compute the Curie constant using Curie-Weiss law. These things you will get to see when you'll see that derivations in the lecture if you have not already seen. So these formulas are directly from there. So once you will go through those derivations and those models, then you will be able to get the origin of these formulas. But here for numerical problems, we will be directly using them. So first question is, compute the Curie constant using Curie-Weiss law. Chi is the susceptibility, T is any current temperature, Tc is the Curie temperature that I explained you, and C is some constant called Curie constant. For paramagnetic material of gadolinium, consider 1 over chi is 20 when temperature is 1400 Kelvin, and 1 over chi is 2 when temperature is 400 Kelvin. So we have to find out the Curie constant using this formula. And sorry, I missed to give the options, and the options, let me just write. Options were A 40.5 Kelvin, B 55.5 Kelvin, C 60.7 Kelvin, and D 75.5 Kelvin. So let's see. So we have already been given this, and we are also given these two cases. So let's see. Let's make equation based on these cases, and then let's see how we can do something with those equations to be able to extract this Curie constant value. So first case is that 1 over chi is 20 when temperature is 1400 Kelvin. The second situation, the second case is 1 over chi is 2 when temperature is 400 Kelvin. Let's put this information in this equation. So for first, it will be 1 over chi is 20. I'm putting in this, okay, 1 over chi 20, and then T minus Tc by C. T here is 1400 Kelvin. Tc, we don't know, it's not given. Divided by C. C we need to find out, Tc we don't know. So we have two unknowns in this equation. This is based on first case, let's call it equation 1. Based on second equation, 1 over chi is 2 and T is 400 Kelvin. Tc we don't know, C we need to find out, it is unknown. This is equation 2. Now if we can do something with these two equations, then we will be able to find out Curie constant. That is what has been asked in this question. So let's try subtracting. Let's subtract equation 2 from equation 1. When we do this, on left hand side it will be 20 minus 2. On right hand side it will be, let's write this, 1400 minus Tc divided by C, and minus this 400 minus Tc divided by C. 400 minus Tc divided by C. On left hand side it will become 20 minus 2, 18, and right hand side denominator is same. So this will be 1400 minus Tc, this is 1, and minus 400 minus Tc. It's better to put a bracket so that when you open the bracket, you won't make mistake in getting the correct sign. Otherwise, you may do mistake here. So here when I open the bracket, it will be 1400 minus TC. This will be minus 400, and this will become plus TC divided by C. Now if we see here, this will be 1400 minus 400, that means 1000, and minus TC plus TC, that will get cancelled. So 4000 divided by C, and on left hand side we have 18, right? So this is our final equation. That means C will be equal to 1000 divided by 18. And when we divide this, for this we can very much use our calculator, because in exam also you will be having your digital calculator. So we don't need to do manually. 1000 by 18 is 55.5, and then it's like 0.5555. It will keep on going. It's irrational recurring. So 55.56, we can round it off. 55.56 Kelvin. This will be the value of Curie constant. So 55.5, that is the most matching here. So B is the correct option. If the options are not there, then of course just directly the answer you need to put. The options were here, I just made, so I put here. This is done. So yeah, I mean, even though here two unknowns were there in this equation, but because we were given two conditions, and thus we could make two equations, and we have to do some kind of arithmetic with those two equations so that we can eliminate one of the unknown and undesirable kind of, so that we can find out the one that we require. So here when we subtracted this TC, we could eliminate, and then the equation was in terms of C. So similar situation you can get where maybe you need TC, then maybe if you divide the C, we can get rid of this C. So you have to see what works well. Anyway, so next question is a circular coil with 250 turns. So number of turns is 250, and area, so it's a coil, number of turns 250. This area of the enclosed by this coil is 2.5 times 10 to the power minus 4 meter square, and the current is flowing in this coil. This is it's a long, I mean, not in this course we have discussed a situation like this, but in very basic, when we start about magnetism, or I mean current induced magnetic field, we know that when we have a current carrying conductor, there is magnetic field around it, and similarly if we have a current carrying loop, then that there also we will have magnetic field because of that. And the magnetic moment due to this current carrying conductor is given by number of turns, the current it's carrying, and the area enclosed by this loop. That gives us the magnetic moment of that current carrying conductor. Anyway, so the current here in this loop is 100 microampere. This is magnetic moment of this, but also we can find out magnetic field due to this at some distance. That also whole set of formula is there. But let's see what's asked here. The coil is at rest in a uniform magnetic field of magnitude B. Okay, so there is uniform magnetic field in which this loop is at rest, so it's not moving. So there is field all around here of magnitude B, 0.85 Tesla, with its magnetic dipole moment mu. As I said, when we have a current carrying loop, it has magnetic moment associated with it. So with this loop, its magnetic dipole moment is mu, which is initially aligned with vector B. So this magnetic field is what they are calling vector. So initially the magnetic moment of this loop is aligned. The magnetic moment of this loop, let's call mu, and this magnetic field B initially they are aligned. Initially they are aligned, and okay, how much work is to be performed on the coil to rotate it 90 degree from its initial orientation. So initially its magnetic moment of this coil is along the direction of B vector. Now if we want to, so this is initial situation, if we want to change the magnetic moment of this coil to 90 degree to the direction of magnetic field, then how much work we need to perform. Sorry, here also the options, let me give you the options. So options were 5.3 microjoule. So how much work needs to be done to move the magnetic moment along the direction to perpendicular to it. So the work done values 2.6 microjoule, 8.3 microjoule, and 9.7 microjoule. Okay, so final is this, initial is this, and the energy. So we know whenever a field is applied to any magnetic moment, there is force acting on it, and there is potential energy term. Either we can write E, we can use the symbol U, anything is okay. But the energy formula is minus of this magnetic moment dot product with the magnetic field vector. This is the formula of the potential energy when magnetic moment is under influence of, or you can say interacting with the field applied. So we have a dot product here. That means this is mu dot B, means this is mu scalar, B, I mean the magnitude, and the dot product of vectors means this is cos theta, the angle between mu and B. If they are aligned, that means here the theta is 0 degree, and when they are perpendicular means theta is 90 degree. So for initially the energy is minus mu B cos 0 degree, and final the energy will be minus mu B. Here the angle will be cos 90 degree, and we need to find out the work done. Okay, now to find out the work done, it will be what is the difference in energy. So final minus initial we'll do. Finally it will move and will be perpendicular to the magnetic field. So work done, how much work we need to do to move it to this position from this position. So what will be the final energy minus what is the initial energy. Okay, let's do this further here. So work done will be final potential energy minus initial potential energy. To change its potential energy from this to this, how much work needs to be done. So this is minus mu B cos 90 degree. Okay, so cos 90 degree, we know cos 90 degree is 0. That means this is minus mu B, and cos 0 degree is 1. So this is minus mu B. Okay, so we can directly write, oh sorry, cos 90 degree is 0. That means this is 0, and cos 0 degree is 1. So yeah, this is minus mu B. This is 0. So E final is 0 minus, and EI is minus mu B. This is minus mu B. That means this is mu B. So this is the work done. Okay. Now magnetic moment, if we need to find out, if we need to do calculation, we need to find out mu. Mu is not given, but I told you this is the magnetic moment associated with the current carrying loop. So we can find out. So to calculate mu, number of turns of coil 250. Then next we need current. Current is 100 microampere. 100. Let's change everything to SI unit. So micro means 10 to the power minus 6. And then area. So area is 2.5 times 10 to the power minus 4. 2.5 times 10 to the power minus 4 meter square. This is the magnetic moment. Okay. And next we need is magnetic field, which is given to be 0.85 Tesla. So the work done directly we can put here: 250 times 100 times 10 to the power minus 6 times 2.5 times 10 to the power minus 4 times the field is 0.85 Tesla. 0.85 Tesla. When we calculate all this, 250 times 100 times 2.5 times 0.85, 53125. Now considering all these exponents, 10 to the power minus 6 minus 4, this will be 53125 times 10 to the power minus 10 0.5, 10 to the power minus 4, 2.85 minus 6, 250, and wait just a minute, 250 times 100 times 2.5 times 0.85. Yeah, that's 3125, this is correct. Then 10 to the power minus 10, this will be Joule for J. Now, because the answers are all in for up to first decimal digit and microjoule, so we need to change it. If I move the decimal point, 1, 2, 3, 4, means 5.3125 10 to the power minus 6 Joule. Okay, because I moved these 4 positions, so 4 decimal, 4 minus 4 gone, minus 6 Joule, and also I can restrict it to first decimal point, then it will be 5.3, and then instead of writing as exponent, I can write microjoule. So the answer here will be option A. 5.3 microjoule is the work required to rotate the coil, whose magnetic moment is along B now, and then we need to finally move it to perpendicular. This is also good question. Okay, next. A paramagnetic gas at room temperature is placed in external uniform magnetic field of magnitude. Okay, first let me write all the options. Option here is 1.23 times 10 to the power minus 6 electron volt, 1.37 times 10 to the power minus 5 electron volt, 1.74 times 10 to the power minus 4 electron volt, and D 1.97 times 10 to the power minus 3 electron volt. These are the options, and in the question, okay, first let's read it. A paramagnetic gas at room temperature is placed in an external uniform magnetic field of magnitude 0.5 Tesla. The magnetic dipole moment of the atom in the gas is 3 Bohr magneton. Calculate the energy difference between parallel alignment and anti-parallel alignment of the atom's moment with external magnetic field. Okay, so either the magnetic moment can lie along the direction of field or opposite to the direction of field. And what is the energy difference? So we have one situation when the moment is parallel to field. Okay, another situation is when it is anti-parallel. The field is in this direction and the magnetic moment is in this direction. Then what will we have to find out the energy difference in these two situations. So one situation is this, and energy in this case will be minus, so this is the general formula, minus mu dot B. For first situation, it will be, we know this cross product, it's minus mu b cos theta. Here theta is 0 degree, here the theta is 90 degree. And okay, so for parallel case, cos 0 degree means 1. So energy will be, let's call EP, parallel. This energy will be minus mu b. And when it's anti-parallel, sorry, it's not 90 degree, it is anti-parallel, means it is 180 degree. So E, let's call it A, anti-parallel. So for second situation, the energy will be minus mu b cos 180 degree. Now cos 180 degree, so 0 degree, 90 degree, or pi by 2 we say, and this we call pi, and this is 3 pi by 2, so 270 degree, this is 180 degree. Cos 0 is 1 and cos 90 is 0, right? If you remember how it goes, cos 0 is 1 and then it becomes 0, sorry, I mean the expansion of, the graph of cos, and then it goes to negative, and then so that is what happens. It becomes maximum at here, and then this is 0, and then cos 180 degree or cos pi is minus 1. So we will get minus 1. This will be mu b. Here it's, in parallel case it's minus mu b, in anti-parallel case it's mu b. What is the difference in the energy here? So in these two situations, what is the difference? So in situation 2, the energy was mu b, and in situation 1, the energy was minus mu b. So the energy difference, I don't know what to call it, let's call it E, the energy difference will be mu b, minus minus means plus mu b. Energy difference is 2 mu b in these two situations, so double. And okay, we need to find out the final value. So 2 times mu is how much? It's given, it's 3 mu b, and Bohr magneton is this. So mu is 3 Bohr magneton. So 3 times, and mu b is 9.27 10 to the power minus 24. 9.27 10 to the power minus 24 joule per Tesla. And then magnetic field is 0.5 Tesla. 0.5 Tesla. When we calculate all this, we'll get 2 times 3 times 0.5 times 9.27, that is 27.81 times 10 to the power minus 24, and yeah, 27 point. Okay, so right now the answer is in joule, because we use this Bohr magneton which was in joule per Tesla. So my answer right now is in joule, and all the options here are in electron volt. So I need to do that. Now we know 1 electron volt is 1.6 times 10 to the power minus 19 joule. So to change this answer from joule to electron volt, I need to divide this. When I divide this by 1.6 times 10 to the power minus 19, it will, I hope it's clear, if I divide this with, okay, that's don't need to, but I mean, if I divide, then it will become 1 joule. So 1 joule will be 1 over 1.6 times 10 to the power minus 19. I hope you can understand how we get this. This will be 1 joule, and 1 joule will be equal to 1 divided by 1.6 times 10 to the power minus 19 electron volt. So that is what I am doing to convert this joule into electron volt. And then it will be electron volt, and let's see what we get. 27.81 divided by 1.6. This confusion why I am dividing, not multiplying, you can ask that also, it's just a simple thing. Okay, so this is 17.381. 17.38 and power is 10 to the power minus 24, and this will become plus 19. Now 19 minus 24 minus 5. 10 to the power minus 5 electron volt. Now, okay, so I need to move because all are after one digit. The decimal point in all options are after first digit. So when I move this, it will be 1.738 times 10 to the power. I divided it by 10. That means minus 4 electron volt. So it changes. Yeah, because I'm reducing I'm moving the decimal to left side. This will become minus 4. 1.74 10 to the power minus 4 electron. C is the correct option here. Okay, our next question. Consider a solid containing the n atoms per unit volume. Each atom has magnetic dipole moment mu. Now solid is placed in external magnetic field B, and each atomic magnetic dipole moment can either align parallel or anti-parallel to external magnetic field. These two situations or options are there. Under this condition, at temperature T, the solid shows the magnitude of magnetization given by this. Okay, so first thing, we don't have to get scared of this big lengthy questions. There's nothing, it's just telling each and everything clearly. That's why it's so long. Okay, so that was the first thing, don't get scared. It's very simple thing. What it's telling, that there is a solid containing n atoms per unit volume. Each atom's dipole moment, let's call it mu, and this solid is placed in external magnetic field B, and the magnetic moment, either it can align parallel to it or it can align anti-parallel to this magnetic field. These two things are possible, and under this condition, what is seen is that this solid shows the magnetization of this much magnetization it's showing. Instead of giving it in a number, we are just giving this expression that this is the magnetization that this material is showing at some T and B. I mean, it depends on if somehow all these values are given, that this is this temperature, this is the magnetic field, then we'll get it in a number form. But here in this question, they have not gone there. They are just putting this expression and telling this is the magnetization of this solid, which is n mu tan hyperbola function of mu b by kbt. This is the expression you must have encountered during the derivations of these ferromagnetic material. Anyways, okay, so this is the magnetization, and then, okay, choose the correct condition for, I need to give the options from the below, for which, so the magnetization is given by this expression. Now for what condition the magnetization will reduce, like due to some reason, right? We always take, if the denominator is very small, then it will just become this, or if it is very something is going to infinity, then it will become 0, like all those kind of situations. The options are there. So for which of that condition the m that is given by this will reduce to n mu square b divided by kbt. So this was what asked in this question. Okay, I hope the question is clear. And the magnetization is given by this, but there are some conditions, I'll tell you now. Out of those 4, under which condition the magnetization will reduce from this to this. So those conditions are, so the conditions are, options are, this mu b is very small than kbt, or it's very large than KBT, or it's equal to KBT, or the last one is none of the above, none of these. Okay, so which of these conditions the magnetization for this material will go from this to this? This was the question. Okay, now we first thing we need to remember, we have to use something of tan hyperbola function. Now tan hyperbola function, if I tell you tan hyperbola of some let's say it's x, some theta or theta, okay, tan hyperbola of theta in terms of exponents, the expansion is e to the power x minus if I'm taking the angle is theta, then it will be e to the power theta minus e to the power minus theta divided by e to the power theta plus e to the power minus theta. It's minus sign in the numerator and plus sign in the denominator. This is tan hyperbola function. Another thing that we need to keep in mind is actually the expansion of e to the power theta is 1 plus theta square by 2 factorial, theta cube by 3 factorial, and so on. So when this theta is very small, that means its square will be even smaller, right? How we know? Just to make it clear, if theta is some big value, if theta is, let's say it's 2, then square of 2 will be bigger numbers, cube of 2 will be bigger number. But if theta is very small, that means some, let's say for example it's 0.2, usually it's even smaller, but here just for example, if say it's 0.2, then square of 0.2 means 0.004, even smaller. So cube will be even smaller. So that's why we say that when theta is very small, its square, its higher powers will be even smaller numbers. So compared to this, they will be even smaller number. So we can always ignore the higher expansions. And then, so the condition when theta is very small, then e to the power theta, we can very comfortably and conveniently just write it as 1 plus theta. We don't need to worry about these higher order expansions. Similarly, for e to the power minus theta, out of the expansion, we can ignore the higher order terms and simply write 1 minus theta. For it, it's minus and plus and minus. Okay. So this is, and then here we saw tan hyperbola theta has this expansion. That means if I substitute by considering, if I substitute that, by considering that theta is very small, and I substitute these expansions here for tan hyperbola, then what will I get is, which was e to the power theta minus e to the power minus theta, e to the power theta minus e to the power minus theta, and in denominator we have e to the power theta plus e to the power minus theta, e to the power theta plus e to the power minus theta. When I open the brackets, I'll get 1 plus theta minus 1 plus theta, and denominator 1 plus theta minus 1, plus 1 minus theta. So this will be 1 cancels, I'll have 2 theta, and in denominator theta cancelled, I'll have 2, that means theta. So tan hyperbola theta can be written as theta if theta is very small. All this I did just to tell you that sometimes we directly take the assumption that if theta is very small, then tan hyperbola theta is equal to theta. How that comes is what I showed you here. I hope this is clear. Now coming back to our question here, because our theta is this mu b by kbt. So all this how we started by considering that theta is very small, and here our theta is mu b by kbt. So if we consider, now the actual solution for the question starts, that if theta is very small, that is if mu b by kbt is very small, that means smaller than 1, then this tan hyperbola theta will be directly theta, right? That's what we saw here. That means magnetization in this situation, magnetization which was earlier this, magnetization expression was this, but if we consider this, then magnetization will be, n will be there, mu will be there, but tan hyperbola, and this will be just this. This is what we derived. Tan hyperbola theta will be just theta. And this will be n times mu square b divided by kbt. This is the same thing that was given here in the question. And we were asked that under which condition magnetization reduces to this. And that is what we got when we considered that this theta is very, very small. Okay, that means, what this means is mu b is very small than kbt, right? We'll send this to right hand side, it will come here. So that means mu b is very small than kbt, then the magnetization will reduce to this. So our option, this first option, is the situation under which the magnetization will reduce to n mu square b by kbt. So this is the correct answer. Option A is the correct answer. Okay. Now next question, question number 5. The magnitude of dipole moment associated with an atom of iron in iron bar. So magnitude is magnitude of magnetic moment of one atom in iron, of an iron in iron bar is basically what they are telling is magnetic moment of iron atom. And it is 2 times 10 to the power minus 23 joule per Tesla. Assume that all the atoms in the bar, so we have an iron bar in which every atom's magnetic moment is this. Assume the atoms in the bar, assume all the atoms in the bar, and they have given dimension of the iron bar which is 5 centimeter long and has a cross-sectional area of, cross-sectional area is 10 to the power minus 4 meters square. Assume all atoms have their dipole moments aligned. So all the dipole moments are aligned in whichever direction, just they are given that they are aligned. What is the dipole moment of bar? Density is given, atomic weight is given. Okay, so this is the magnetic moment of one atom. We need to find out how many number of atoms are there in total to tell that what is the total magnetic moment of this this iron bar, because total magnetic moment will be magnetic moment of one atom multiplied by number of atoms. Magnetic moment of one atom value is given. We need to find out how many atoms are there in this iron bar to tell what is the total magnetic moment of this iron bar. Okay, so total number of atoms we need to find out. Now number of atoms, we know, we have this formula, mass times Avogadro number divided by atomic weight of iron, and this is mass of this iron bar. The mass of iron bar, is not given. That means we need to use density and volume here. Okay, let's first calculate mass. So we know density of any material is given by mass upon volume. Here we have been given density and we have been given dimension of this bar, so we can find out mass from that. So mass will be density times volume. Okay, if I put mass will be, yeah, density times volume. If I put it here, then number of atoms will be density times volume times Na divided by atomic weight. Okay, now density is 8000 kg per meter cube. Let's keep in mind to keep everything in SI unit. So kg per meter cube is okay, 8000. Now volume of this iron bar, length times breadth, this is a cylinder, so area times the length or the height, whatever you call it. Area is 10 to the power minus 4 meter square, 10 to the power minus 4 meter square, and length is in centimeter. We'll change it to meters. 5 centimeter, that means 5 10 to the power minus 2 meters. Yeah, 5 times 10 to the power minus 2 meter. 5 times 10 to the power minus 2. So overall it will be meter cube. This will be the volume. So here I'll put 5 times minus 4 minus 2 means minus 6. 10 to the power minus 6 meter cube, and Avogadro number 6.023 times 10 to the power 23, and atomic weight is 55.85 in gram per mole, right? Either we call it at atomic weight, either the unit is AMU, atomic mass unit, or it's also called gram per mole. Now here, to keep everything in SI unit, we'll change it to kg per mole, and when we'll do that, gram to kg will be 10 to the power minus 3 conversion, right? So atomic weight, which is 55.85 gram per mole. When I'll convert it into kg per mole, I'll have to multiply 10 to the power minus 3. Okay, all this is done. Now when I'll do calculation, 8,000 times 5 times 6.023, 6.023 divided by 55.85, answer is 4313.6974, and the powers 10 to the power minus 6 plus 23, then this, which is plus 3, so it will be 3 minus 6 minus 3, so 20. 4313.7, 10 to the power 20 number of atoms I have got. Now further, what we had to calculate dipole moment. So for dipole moment, magnetic moment of each atom I am given already. I just needed number of atoms. Now I have got number of atoms, so I can just multiply. So total magnetic moment of this iron bar will be, magnetic moment of one atom was 2 times 10 to the power minus 23, 2 times 10 to the power minus 23, and number of atoms we have got 4313.7, 4313.7 times 10 to the power 20. This will be times 8627.4 times these powers 10 to the power minus 23 plus 20. 8627.4 times 21 is 23, 10 to the power minus 3. This will be joule per Tesla. And do I need to convert it into electron volt? Oh, sorry, I need to give you options, right? We have to write options for this, let me write here. So options were 7.9 ampere meter square, 7.9 ampere meter square, 8.6 ampere meter square, or 9.8 ampere meter square, or 11.8 ampere meter square. So here, yeah, our final answer in joule per Tesla or simultaneous unit we have ampere meter square, so no problem. So we don't need to convert to anything else, everything is fine. And so just I need to maybe just shift these decimal points. Just a minute. Yes. -3. This will be 1, 2, 3. But if I move the decimal point, it will be 8.6274 times 10 to the power 3. And I have already 10 to the power -3 joule per Tesla. That means this will be 8 point, if I just round off, maybe 63 times this is 10 to the power 0 means 1 joule per Tesla, and I have told this is already also equivalent to ampere, ampere not per, sorry, ampere meter square, the another unit of magnetic moment, right? When we say we have a current current carrying coil, then the magnetic moment we say NIA, so that SI unit ampere meter square comes from this. But usually when we define magnetic moment, we also use joule per Tesla when we do Bohr magneton derivation. So they are equivalent. So yeah, final answer will be 8.63 ampere meter square. 8.63 ampere meter square. B is the correct option. Okay, question number 6. The saturation magnetization of the ferromagnetic metal nickel. This nickel is a ferromagnetic metal, and its saturation magnetization means, I had told you in ferromagnetic materials graph, right? It is the maximum magnetization that a material can show, because that at that point all the magnetic moments get aligned. No randomization is there. So saturation magnetization means the maximum magnetization can become. That is what is saturation magnetization. Okay, so the value of saturation magnetization, or okay, we can write it like M maximum also, because it's here given. The value is 5 times 10 to the power 5 ampere per meter, unit of what is this, magnetization, because magnetization we also say magnetic moment per unit volume, right? Magnetization, and moment, like I said, ampere meter square, if I call it like this, then divided by volume means my meter cube, and what will it become? Ampere per meter. So if we use this derivation of moment, then magnetization is in ampere per meter, and this was extra information. So this is the value of saturation magnetization for ferromagnetic metal nickel. Calculate the magnetic dipole moment of single atom. This is the magnetization. Now we need to know the magnetic moment of single atom. Okay, so here also, like not last time, like last time we were given magnetic moment of single atom, and then we had to find out for the whole material. So here we know for the total, and we have to find out for one. So how we'll do this is, because it's magnetization given, not magnetic moment. So see, if total magnetic moment we are talking about, then it will be magnetic moment of single atom, and number of atoms, total number of atoms. But we are given magnetization, which is it is usually denoted by capital M, and magnetic moment sometimes we denote by small m also. So magnetization is magnetic moment per unit volume. So what we can write it as magnetic moment of one atom and number of atoms per unit volume. Okay, and this sometimes we denote as small n, that number of atoms per unit volume. Okay, so because magnetization is given, so we need per unit volume aspect here. Okay, I hope this is clear. Now to get number of atoms per unit volume, it will be it will be density times Na, because for number of atoms I need mass. Let me start from there. Mass times Na. For number of atoms I need mass times Na divided by atomic weight. Okay, and mass I know is density times volume, so this will become like this. Okay, but I don't need to find number of atoms. What I need is number of atoms per unit volume. That means if I divide by volume on both sides, then I'll get number of atoms per unit volume, which will be, if I divide this by volume, this will be gone, right? So it will be density times Na divided by atomic weight. I need to find small n, which is density times Na divided by atomic weight. Density is 8.9 gram per cc. I need to change it to kg per meter cube. Do I? Yes, because this is in SI unit. But I think everything I should put in SI unit. So 8.9 gram per cc. And actually the options are also in SI unit, I will tell you. So I need to change this also into SI unit. So density, which is given to be 8.9 gram per cc. This cc is actually, cc means centimeter cube. Okay, so it's gram per centimeter cube. So when I change 8.9 gram to kg, when I change, it will be 10 to the power minus 3. 1 gram will be 10 to the power minus 3 kg, and 1 centimeter is 10 to the power minus 2 meter. So I mean, just like 1 gram is 10 to the power minus 3 kg, and 1 centimeter is 10 to the power minus 2 meters. So 1 centimeter cube means 10 to the power minus 2 whole cube meter cube. That means 10 to the power minus 6 meter cube. That means this density will become 8.9 gram changes to 10 to the power minus 3 kg divided by 10 to the power minus 6 meter cube. This is cube. Okay, I can write it like 8.9 times 10 to the power minus 3 plus 6 kg per meter cube. 6 minus 3 is 3. So 8.9 10 to the power 3 kg per meter cube. Okay, finally, this is the density. 8.9 times 10 to the power 3 kg per meter cube. Avogadro number 6.023 times 10 to the power 23. Atomic weight given in gram per mole. When I change it to kg per mole, it will be multiplied by 10 to the power minus 3. 58.71 times 10 to the power minus 3. Okay, so this is done. Now if I calculate all this, I'll get 8.9 times 6.023 divided by 58.71 is 0.913 times 10 to the power, what was it, 3? 10 to the power 3 plus 23, and this will be 3. 10 to the power 29. And if I shift by 1, then it will be 10 to the power 28. Number of atoms per unit volume. So I can write per meter cube. Atoms per meter cube. So this is I got. Now I need to find out this, and magnetization I know. So to find out this, magnetization divided by number of atoms per unit volume. So this was the formula, right? Number of atoms per unit volume. Magnetization I know. This I have calculated. Now I can find out what is the magnetic moment of one atom. So this will be magnetization value was given, which was 5 times 10 to the power 5. 5 times 10 to the power 5 ampere per meter, and number of atoms per unit volume is 9.13. 9.13 times 10 to the power 28 per meter cube. When I do the calculation, 5 divided by 9.13, this will be 0.5476 times 10 to the power 5 minus 28 ampere per meter. 5 minus 28. 5 minus 28 means 10 to the power minus 23. 10 to the power minus 23 ampere per meter. And if I move this decimal point, it will be 5.476 10 to the power minus 24 ampere per meter. Okay, so I think I didn't tell you the options, sorry. So the options were options for this questions were 5.47 times 10 to the power minus 24 ampere meter square, or B 9.27 times 10 to the power minus 24 ampere meter square, and the C option was 7.15 10 to the power minus 23 ampere meter square, and D option was, I should write the option first, 9.89 times 10 to the power minus 23 ampere meter square. So our answer matches this. This is magnetic moment, it's not magnetization, and this was in ampere per meter, right? And this was in per meter cube. So this will become ampere meter square. Okay, so our answer is 5.5 something 10 to the power minus 24. Yeah, this first option. 5.47 10 to the power minus 24 is the correct answer, option A. Okay, next question, question number 7. Measurements in mines and boreholes indicate that Earth's interior temperature increases with depth of average rate of 30 degrees centigrade per kilometer. Means if this is Earth, round, and as we go deeper, Earth's temperature increases by 30 degrees for every kilometer that we go to the core or to the center of Earth. If this is center, for every 1 kilometer that we go towards the center, the temperature increases 30 degrees centigrade per kilometer. Assuming surface temperature is 10 degrees centigrade, means at surface the temperature is 10 degrees centigrade, and then for every 1 kilometer it increases by 30 degrees centigrade. What depth does iron cease to be ferromagnetic? Consider Curie temperature for iron is 770 degrees centigrade, and it varies very little with pressure. Yeah, because when we'll go inside, pressure will be increasing, but here we have to consider that pressure will not have very much effect on the Curie temperature. That is what we have to assume. We have to only worry about the temperature and then tell that at which distance the iron will lose its ferromagnetic nature and will become paramagnetic. That means what is its, at which distance from the surface the temperature will be equal to Tc, and at that point the ferromagnetic nature will be destroyed, we can say. So that temperature Tc here is given 770 degrees centigrade. So at this temperature iron will lose its ferromagnetic nature, and we need to find out if the surface temperature is 10 degrees centigrade, then at what distance from the surface the temperature will be 770 degrees centigrade, because that is what has been asked, that when the iron will cease to be ferromagnetic. That means when the temperature becomes Tc, because we know when the temperature crosses Tc or is equal to Tc, the material loses its ferromagnetic nature. So at what distance, let's call it x, at what distance from the surface the temperature becomes 770 degrees centigrade. Okay, this is the question. Now at distance x, the temperature, the final temperature will become 770 degrees centigrade. Okay, initial temperature, I mean at the surface, the temperature is 10 degrees centigrade. So final temperature will be initial temperature plus 30 degree per kilometer, 30 degrees centigrade per kilometer is the increase, multiplied by the distance x. Say at after x distance plus the initial, because initial is not 0, it is 10 degrees centigrade. So after, because the rate of increase of temperature is 30 degrees centigrade per kilometer. So if after x kilometer, the final temperature will be Ti plus 30 degrees centigrade per kilometer multiplied by x kilometer, and that will be equal to 770. I hope this equation is clear. If you have doubt, I can explain this again. Initial is 10 degrees centigrade. This will be 30 times x, and finally 770 it will reach. So I can find out x, the position. This will be, x will be equal to 770 minus 10 divided by 30. So this will be 760 divided by 30. 760 divided by 30 in kilometers. So 760 divided by 30 is 25.333 kilometers. 25.3, oh sorry, the options for this question is, options, let me write here. The options for this questions were 14.7 kilometer, 20.5 kilometer, C is 25.3 kilometer, D is 30.6 kilometer. At what distance from surface we'll reach 770 degrees centigrade? And the answer is option C. Okay, question number 8. Calculate the diamagnetic susceptibility of copper, assuming that each atom of copper contributes only one electron for its diamagnetic property, and the mean square distance of electron contributing from nucleus is equal to, then we take radius also, so it's okay. Mean square distance of electronic contribution from the nucleus is equal to the radius of monovalent copper ion, or radius of copper ion, and lattice constant of copper is this, and radius of copper is this. So this is 0.90 angstrom given. And we need to find out diamagnetic susceptibility. This we can directly take the formula. from the when we had taken the model for deriving diamagnetic origin. That time we had obtained this formula. So directly let's take this formula. So minus n mu b, z is at, like how many electrons are contributing, and it's given that each atom is giving one electron. So maybe z will be 1 here. E square of this, sorry, these are all multiplied, and times 6 times n mass of electron. After putting, this is number of atoms per unit volume per meter cube. This is Bohr magneton. This, as I told, it's a number of electrons available. So every atom is giving one electron. E is the charge of electron. R is this distance, 6m. Putting all these values here. So for n, number of atoms per unit volume, we are talking about copper. Okay, and copper is FCC, and we have discussed this several times that FCC unit cell has 4 total number of atoms, 1 contribution coming from all the atoms sitting at the corners, and 3 atom contribution, total 3 atoms we get from 6 atoms sitting on the face. So for FCC we have total 4 atoms, and the volume will be A cube. A is this lattice constant of copper. So this will be 4 divided by 3.61 times 1 angstrom is 10 to the power minus 10 meter cube. Okay, this will be this. Now putting all these here, Bohr magneton value is, or let me first calculate this n. This will be 3.61 to the power 3, 47.04. This 10 to the final answer here will be 8.5 times 10 to the power 28 per meter cube. This is number of atoms per unit volume. Putting that directly, let's go to the next slide. Diamagnetic susceptibility will be, when I put the value here, minus 8.5 times 10 to the power 28, and then we need to write this permeability. This is not Bohr magneton. So this formula, this is permeability, relative permeability, which is 4 pi times 10 to the power 7, and then number of electrons 1, because every atom is contributing 1, and then charge of electron 1.6 times 10 to the power minus 19, and then we have this mean E square. This is E square, and then this is 0.9 and angstrom to meter, so it will be 10 to the power minus 10 whole square. And then in denominator we have 6 times mass of electron, which is 9.1 times 10 to the power minus 31 kgs. Then I will do all this calculation. I'll get 8, 5. I will go to 4 times. Okay, multiply by 6. 6. 4.05, and all the powers, minus signs there, all the powers 10 to the power 28 plus 7, this will be minus 28 this will be minus 20, and this will be plus 31. So minus 4.05, and this will be, okay, let me do 27 minus 20, 30. This will be 10 to the power, wait, this is correct, huh? 28 and 20. Oh, sorry, this will be 30. This will be 30. 19 square will be 30. Sorry, so what will be the total? Let's see, 28 plus 7 minus 38 minus 20 plus 31. This will be 10 to the power 8. Hope everything is correct. That's what I'm getting. Is there something wrong in some power? I think so. Anyway, so yeah, I mean, this is our answer. Minus 4.05 times 2. This is option, our final answer. Okay, question number 9. The electronic configuration of chromium ion, chromium 2 plus, is 3d4 4s0, means the valence electron is in d orbital. 1, 2, 3, 4, 5. Yeah. This is the azimuthal quantum number, right? I mean, this for orbital angular momentum. 3d4 means 1, 2, 3, 4. Okay. Calculate magnetic susceptibility. Okay, magnetic susceptibility for paramagnetic salt. So for paramagnetic material, the susceptibility, magnetic susceptibility, is calculated by permeability multiplied by this number of atoms per unit volume, number of atoms, and effective magnetic moment, and then Bohr magneton, square of Bohr magneton divided by 3 kBt. So we need all these things. So to get mu effective, we need S. Okay, so when from here, what S we'll get? We'll get 2 times 1, 2, 3, 4. We have 4 unpaired electrons. Sorry, not 2, half. Because one magnetic moment has half spin, right? We have 4 unpaired electrons. That means half times 4. That means 2. S is 2. So magnetic moment will be 2 under root S plus 1. That means 2 times 3 means 2 root 6 will be mu effective. Okay, permeability will be 4 pi. Don't get confused, one is permeability, one is magnetic moment. We use mu symbol for both, so just try to keep in mind, don't get confused. Permeability is 4 pi times 10 to the power minus 7, and this is Avogadro number 6.023 in kg, so it will be 10 to the power 23, and then mu effective square of mu effective means I can write it, square of mu effective will be square of this, means 4 times 6, 24. Oh, sorry, this is in formula, this is also in square, this is also in square, and then square of this Bohr magneton means, I should write it here actually, and then Bohr magneton means 9.27 times 10 to the power minus 24 whole square, and in denominator we have 3 times kb. kb is 1.38 times 10 to the power minus 23, and temperature, which temperature, at 500 Kelvin. When we do all this calculation, we'll get 4 4 6.023 times 24 7 divided by 3 divided by 1.38 divided by 500. That is the final answer after calculating all this. Chi for paramagnetic material will be 75.37, and now the powers. So it will be 10 to the power minus 7, oops, minus 7, and then plus 23, plus 23, and then 10 to the power minus 48, minus 48, and this will be plus 23 plus plus 23. That's it. Yeah. So this will be 75.37, 10 to the power, let's calculate, minus 7 plus 23 minus 48 plus 23 minus 9. And if I shift the decimal point, it will be 7.54 times 10 to the power be one mistake. If not, this will be much. If I'm dividing by 10, 10 to the power minus 8, 10 to the power minus 8. I think one mistake is having in this. Here I need to put it into kg. So in one, I mean it's gram per mole, right? In kg per mole, when I will convert it, this will be 10 to the power 23 and 10 to the power minus 3. Okay. And then this will be minus 5. And this will be the answer. Okay. Next question is, europium oxide is ferromagnetic with the Curie temperature of 70 Kelvin. This is some material which is ferromagnetic and its Curie temperature is 70 Kelvin. And europium ion has total orbital angular momentum 5/2 and G is 2. Calculate the intrinsic magnetic flux density when T tends to 0 Kelvin. Okay. Okay, so we have to find out intrinsic magnetic flux density, that internal field thing. And you know, intrinsic from the Weiss molecular field theory, intrinsic magnetic field density is given by this formula. A function of T, magnetization, right? And this is some constant. From this derivation of this theory, this internal field or this intrinsic flux density, the formula is given by this constant, n number of atoms per unit volume. Lambda G factor is total orbital angular momentum, Bohr magneton, and this is Brillouin function that you must have seen in the derivation today. I mean this week. This is Brillouin function. Okay. Now we have to find this out for T tending to 0 Kelvin. So for T tending to 0 Kelvin, that means X will be going to infinity. This you can understand if you have already gone through the derivation. Okay. For T tending to 0 Kelvin, this is 0 Kelvin, X will go to infinity, and when X will go to infinity, that means this Brillouin function will go to 1. Okay, and in that case this intrinsic flux density value will become reduced to this. Okay, now we need to substitute these to find out this. Okay, J is given, G is given, Bohr magneton value we know, lambda we don't know. Okay, so but we have been given Tc, so we can use another formula. I mean, we can use one more thing. We need to find out this, but we don't know lambda for this material. But we have another formula after deriving more further in this theory, that Tc, the Curie temperature, is equal to lambda n g square mu b square j plus 1 divided by 3 kb. Okay. From this, we can understand that how we can write this, because this lambda is there, n times g, 1 g is there, j is there, 1 mu b is there, so I can write this Tc as some product of Be also, right? So I can write Tc as Be, and what is remaining now is 1 g, j plus 1, and 1 mu b, and then denominator. So I can write it like this. 1 g was there, and then mu b was there, 1 extra j plus 1, not extra, I mean that j plus 1, and in denominator we had 3 kb. So Tc, which formula is this, we can write it as Be times all this, and Tc we know. So I could clearly avoid here the value of lambda, which was unknown. That is why I use Tc formula here. Okay. Now finally I need to find out Be. Be will be equal to Tc multiplied by 3 kb and g mu b j plus 1. Now let's put these values. Tc is 70 Kelvin. 3. This is kb is 1.38 times 10 to the power minus 23 divided by g is given, which is 2. Bohr magneton is 9.27 times 10 to the power minus 24, and j plus 1, j is 5 by 2, so j plus 1 means 7 by 2. 7 by 2. When I will do this calculation, times 3 times 1.38 divided by 2 divided by 9.27 divided by 4.466, and the powers now 10 to the power minus 23 plus 24. It means 10 to the power 1 means 44.66. 44.66 Tesla. This is the magnetic field value for this. Okay, next question is, consider ferromagnetic material nickel having lattice constant 4 angstrom. Nickel ion has 8 electrons in 3D shell. 3D shell means 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons in 3D shell for Ni2 plus. It has FCC structure and lattice constant is 4 angstrom, and determines saturation magnetization assuming quenching of orbital angular momentum. Okay, so I don't know if you know or not, when we calculate orbital angular momentum from this formula, not for all elements, this when we take ml from here and then we get orbital angular momentum from Hund's rule, right? The problem is there are some atoms like d orbital atoms, and here this is nickel also d orbital, which experience orbital quenching. So there is a phenomenon known as orbital quenching. Okay, what this means is that orbital angular momentum for some atoms, some elements, it becomes zero, and this happens when the electric field of neighboring atoms influence the or changes or reduces the orbital angular momentum to zero. The orbital quenching is the reduction of orbital angular momentum to zero because of the electric field of neighboring atoms. That is called crystal field theory. Depending on what kind of atom arrangement is there around that particular atom that we are talking about, the orbital angular momentum can quench, can diminish, can become zero. So that is what we know as orbital quenching. So when we talk that some material is experiencing orbital quenching, especially like for d orbital material, that means orbital angular momentum is taken as zero. Okay, so here we need to find out saturation magnetization for this material. Okay, let's go directly to the formula. So the formula for magnetization for this ferromagnetic material will be N, number of atoms per unit volume, Landé G factor, this is J, which is total orbital angular momentum, and Bohr magneton. This is the formula for ferromagnetic material. This is just multiplication. Okay. We need to find out N here. It's FCC, that means 4 atoms are there in unit cell. Volume A cube. Okay, so let's calculate this. 4 divided by 4 angstrom. 4 times 10 to the power minus 10 and cube of this. So this will be 4 divided by 4 cube means 0.0625. 10 to the power 30 atoms per meter cube. This is done. Now G. G we need to calculate. To calculate G, we need the value of L, we need the value of S, we need the value of J. Orbital angular momentum, spin angular momentum, total angular momentum. That we'll get from this electronic configuration. Because it's been told that nickel has orbital quenching, that means L is 0. How to find out spin angular momentum? Let me write here again. Ni2 plus has electronic configuration of 8 atoms are there, right? 1, 2, 3, 4, 5 orbitals and 8, 5, 6, 7, 8. So L is 0 because orbital quenching. S, number of unpaired electrons. Okay, multiplied by half because one moment has half spin. And how many unpaired? This is paired, this is paired, this is paired. We have 2 unpaired electrons. That means S is 1. Now J. So from Hund's rule, this you must have studied. If Hund's rule has tells us how we arrange the electron in this for ground state. Also, it tells how we calculate J. One situation is if the number of atoms in this valence shell is less than half, then J is L minus S. If number of electrons in the valence shell, this orbital, is more than half, then J is L plus S. So here we see that total number of electron that can occupy d orbital total is 10, because there are 5 orbitals, each can occupy 2. So total 10 electrons can be here, and here there are 8 electrons, means more than half. So we will use J is equal to L plus S. L is 0, S is 1, so J will be 1. So from this we can find out Landé G factor. The formula is 1 plus J, J plus 1 plus S, S plus 1 minus L, L plus 1, but L here is 0 anyway, and in denominator we have 2 J, J plus 1. Okay, so this is anyway 0. Let's put the values here. So G will be 1 plus, and J is 1. So 1 plus 1 means 2, right? 2, and S plus 1. S is also 1. So 1 plus 1 means 2, and L is 0. In denominator, we have J is 1. So 1 and 1 plus 1, 2. 2 times 2, 4. So 1 plus 4 by 4. 1 plus 1, that is 2. So G is 2. We have calculated N, we have calculated G, we have calculated J. Bohr magneton value we know, so we can find out magnetization for this ferromagnetic material. So magnetization here will be N G J mu B. N we found out it was 0.0625. 0.0625 times 10 to the power 30, 30 per meter cube. G is 2, J is 1, yeah, J is 1, and Bohr magneton is 9.27 times 10 to the power minus 24. When I will calculate all this, I will get 0.0625 times 2 times 9.27, 1.159, and powers 10 to the power 30 minus 24 ampere per meter magnetization will be, and this will be 1.159 10 to the power 6 ampere per meter, which is the correct answer. So this was some good questions, I would say, based on the concepts discussed this week. And I hope I try to explain every question, how we are getting, how we are approaching. I hope everything is clear. If there's no question, we'll end today's session. If you have doubt, you can ask either in discussion forum or in next class or this class. Also, I think most probably we'll have some extra session also. If you have doubt, you can ask things there as well.